Math with Dave.
Well, hey everybody, it's Dave here, and today we're going to have our first lesson in a series of lessons on this whole concept of radicals and how to manipulate them, solve for them, things of that nature. I highly recommend for anybody watching that if you really want to be successful at these, you should brush up on your exponent rules, as you'll notice that when I talk about radicals, I speak of these often. It's a good idea to know the definitions of all the numbers we're talking about here. The entire thing, of course, is called a radical. The number underneath is a radicand. At the same time, we hardly ever use that terminology. But the number inside the radical but out front is called the index. Don't confuse this with a coefficient, which is a large number in front of the radical. This number actually means which root we are taking. If there's no number there, the implication there is it is a square root. Outside of that, look for 3, 4, 5, or any other number for that matter, which will tell you whether it's a cube root or beyond. Please don't make that mistake. We'll do a couple of different types of operations early on with radicals. We're either going to take it from a mixed radical, which means a coefficient out front of the radical, or an entire radical where everything's just underneath the radical. If we take a look at a question like 7 times the square root of 2, you just have to remember that at one time that 7 was underneath the radical as a different number. The easiest way to think of this is the fact that you had to perform the operation that you're trying to put it back into in order to get that number out front. So what does that mean? That means that that wasn't really a 7. That was the square root of 7 times 7. And that root 2 didn't change at all. And 7 times 7, as we know, is 49. And this is where exponent rules would help out a lot, because we should know that if it's a different base but the same exponent, you can actually combine those things together to end up with the square root of 49 times 2, which is equal to the square root of 98. So that's what we mean by an entire radical. We have a number underneath, no coefficients out in front. And again, you don't need to show all of these steps, but you should certainly show at least an understanding of the idea that that 7 was once a 49 underneath the radical, but in order to pull it out of the radical, you had to take the square root. So the same thing holds true for b, except this time we're dealing with variables instead of numbers. It really doesn't change what we did, but in this case, it's not a to the 4, it's actually a to the 4 squared times the square root of a. Well, again, exponent rules helps out here. A to the power of 4, all that squared is equivalent to a to the power of 8 times the square root of a, and this gives you the square root of a to the power of 9. So again, really important to know your exponent rules, because those will become really important as we do this reduction stuff. And if you think that this is easy and that, we can just get to the next lesson, a lot of this stuff is going to be required for the future lessons. So if you can't do this stuff inside and out, you're really going to have a hard time with the future stuff. C is the first tricky problem, because instead of a square root, we have a cube root, which means whatever we did to take a number out to get 5b, we had to cube root it to do so, which means 5b isn't really 5b when it's underneath the radical. It is 5b cubed times the cube root of 3b squared. And now we can actually perform the cube of the 5b. So remember that cube applies to the b and the 5. So 5 cubed is 125. B cubed is, of course, b cubed times the cube root of 3b squared. Now we can multiply the numbers and multiply the variables. 3 times 125 is 375, and b cubed times b squared is just b to the 5th. Common mistake that's made there is they either don't cube the 5 initially to get that 125, or when they multiply the cube b cubed times b squared, they give yourself b to the 6th. So please remember that all of this requires some exponent rules that you absolutely have to know. If we go the other way around, well, all we need to do is what we've just done, but backwards. In the first part there, we had the perfect squares, and we just had to square them back. But in this case, we have to find the perfect squares and then pull them out. So in the example that I've given there, the square root of 18, well, the easiest way to think about this is to think about all the multiplication factors of 18. So we have 1 and 18, we have 2 and 9, and we have 3 and 6. Well, out of all those, what we're thinking of is perfect squares. So remember that perfect squares: 1, 4, 9, 16, 25, 36, 49, etc. And anytime we have a radical that we're trying to reduce, these are the numbers we're looking for when it's a square root. Another idea to think of would be for cubes. You want to be thinking of 1, 2 cubed is 8, 3 cubed is 27, and so on. Just think of the first like 4 or 5 perfect cubes. Certainly all the perfect squares up to 12 squared, even 13 squared may be useful. But you'll notice there that, hey, look, there's your perfect square, which is just 3 times 3, which gives us our answer of 3 times the square root of 2. So every time I do these questions, I'm going to be looking for the highest perfect square I can get times whatever number was required, and then we can solve from there. If you can't think of the highest perfect square, just find the first perfect square. And what you'll end up with is a number in the radicand that will actually still be reducible after the fact, which isn't a horrible thing, it just means more steps. So the first one here, we have the square root of 200. Well, we know, hopefully, that 200 is 100 times 2. And now we'll just do what we did with the other one, but opposite. We'll separate this into the square root of 100 times the square root of 2. Well, the square root of 100 is a perfect 10 times root 2. I put the dot in between to show the multiplication, but typically they'll just write it as 10 root 2. Easy peasy. Where it gets a little tricky now is when we start dealing with variables. But variables don't have to be too hard so long as we remember one thing, that the way that we find a perfect root, whatever root that is, if it's a cube or a quad root or whatever, is we look at the index or the power of the number under the radical and we ask ourselves, is it divisible evenly by the index? Because if it's not, I need to split it up so that the number that I end up with is divisible evenly by the quad root. Again, this is exponent math at its best. So c to the power of 9 isn't going to work, but if I take the quad root of c to the power of 8 times c, well, c to the power of 8 times c is still going to give me c to the power of 9, but look what I can do now. I can split up c to the power of 8 times the quad root of c, and now I have this particular term here, and I know that what times what times what times what gives me c to the power of 8? Well, that is just c squared times the quad root of c. A really nice way to think about this is if I write it as an exponent, this is going to give me c to the power of 8 over 4, which gives me c squared. And that's exactly the reason why I rewrote it like this, is I knew that I needed to find that nice even number that I could divide 4 into evenly to give you an answer. If this were the cube root of c to the power of 9, well, 9 is divisible by 3 evenly, and we would have been able to get c cubed very quickly. In C now, we just have to deal with the numbers and the variables separately. So I'm going to rewrite it as the square root of 48 times the square root of y to the power of 5. If I deal with 48 first, it may not be obvious right away, but eventually you'd come up with the idea that 16 times 3 gives you 48. And with y, remember that there's no number in front of that radical, which implies that it's a square root. 5 is not divisible evenly by 2, but 4 sure is, and that gives me a times y after the fact. Well, now I can write the first one. Well, the square root of 16 is 4, and I'm left with the root 3, and then the square root of y to the power of 4 is y squared, and I'm left with the square root of y. This would get you almost full credit, but the problem is you've forgotten one final thing. You got to take these two radicals and you've got to combine them together, because those are both reduced, but if we multiply them now, we have 4 times y squared. Oh my goodness. We have 4 times y squared times the square root of 3y. This is the more correct answer because, again, you've taken everything and you've combined things together to get your final result. So, again, just because you understand how to reduce them doesn't mean that you're going to write the answer the correct way, because, again, you still have to combine them together when you're done. All this taken into effect, you may run into questions like this where you have to order radicals into the order of greatest to least or least to greatest without a calculator. A lot of teachers tend to have two parts to a test where it's one without calculator, one with calculator. And when you look at something like this, you need to think entire radical, because it's a simple process. The square root of 21 will be less than the square root of 22, which will be less than the square root of 23, etc., etc. So when I see this question and I see this square root of 23 there, I know that I'm going to need to take all of these and rewrite these as entire radicals. So 5 is a little interesting because it's not really a radical at all, but remember that 5 is really just the square root of 25. If we look at 3 root 3, remember that's the square root of 3 times 3, which is 9 root 3, which is just equal to the square root of 27. This is just the square root of 2 times 2, which is 4, times the square root of 6, which is just equal to the square root of 24. And of course we have our original entire radical. Now you can see that we have a root 23, 24, 25, 27. This now allows us to write these from least to greatest because we have them all in our entire radical form. So we have the square root of 23 as the least, followed by the square root of 24, which is actually 2 root 6 in the problem, followed by square root of 25, which is just 5, and finally the square root of 27, which is just 3 root 3. Don't forget to write these in their original form, not in their entire radical form. The problem with radicals is they're not always going to be real values. The mantra you need to think of anytime you think of square rooting a number is I can't find the real root of a negative number. What does that mean? It means if I try to take the square root of -4, I won't end up with a real answer. I'll end up with this idea of I, which is not what we're dealing with in this case. At the same time, if you take the cube root of a negative number, that is more than realistic, because if we have something like the cube root of -8, well, -2 times -2 times -2 will give you a -8. So you just need to remember that whenever it's an even root, if you try to take the square root or the quad root of an even number, you will only end up with an even root. There will be no such thing as taking the quad root of -16. So what does that mean? That means when we have a radical question such as this, the simple process is take a look at the radical. In this case, so what does this mean? It means we just take a look at the radical and we look at whatever's underneath the radical and we ask ourselves, okay, for what value of x is it going to be greater than or equal to 0? And again, for those that can't remember with the inequality symbols, you basically treat it like an equal sign, with the exception of if you are dividing both sides by a negative number, you have to flip the inequality sign because you've now changed what part of the number line you're talking about. But in this case, I'm just going to add 2 to both sides. I'm going to get x has to be greater than or equal to 2. Well, that should make sense, because if I put in x is equal to 2 underneath the radical, I get 0. If I put 1 underneath the radical, I get -1. That's a no-no. But if I get 3 and I put under the radical, I get a +1, which I'm allowed to do. So that restriction completely makes sense. If we look at our second question here, we need a restriction that satisfies both radicals, which means we have to look at both and then decide if there are any values where this is possible. So if we have x minus 5, we know that x minus 5 has to be greater than or equal to 0. So x has to be greater than or equal to 5. But at the same time, 1 minus x has to be greater than or equal to 0, which means that 1 has to be greater than or equal to x, or written a different way, x has to be less than or equal to 1. Great. So now I have to find values such that it satisfies both of these restrictions. The idea that x has to be greater than 5, but less than 1. And I would think that all of you at this point recognize the fact that there is no value that satisfies both those inequalities. So this is flat out not possible. And that's a key, is just finding the restriction underneath individual radicals is one thing, but now being able to look at both radicals and come up with a range of values for which they are possible is another thing. So be careful with those moving forward. We'll do a bunch more of those later on. So we've gotten to the point now where we should be able to add or subtract radicals willingly because we know how to reduce them, and as long as we remember that the radical has to be the same when we add or subtract, it's the same idea as a variable. So you can't take the square root of 3 and add the square root of 2 and get some nice number. There's no general rule that allows you to do that. But if we look at something like a, well, the square root of 50, well, that's so if we look at a, we see the square root of 50. Well, we can rewrite this as the square root of 25 times 2, and this is already in its mixed radical form, and this will now reduce to 5 root 2 plus 3 root 2. So again, this is just like a radical. You have 5 of something and you have 3 more of the same thing. That gives you 8 root 2. Okay, so reduce down to the lowest radicand you can, and then see if they combine. Just don't be afraid to not combine them if they don't work out that way, because a lot of times people will just try to squish things together, which works great with multiplication, but with addition and subtraction, not so much. So we look at b now, we see that, okay, we have the square root of 4c. Well, we can't square root c, but we can square root 4. 4, the square root of it is just 2. And so we have 2 root c minus, we have that 4 out front times, well, the square root of 9 is 3, and we're just left with the square root of c. This right here is just the restriction on the radicals. That's okay. Well, don't screw this part up right here. If we have subtract 4 times 3, that's the same as 2 root c. Subtract 4 times 3 is 12 root c, which gives you the answer of negative 10 times the square root of c. Okay, so again, reducing it is one thing, but then actually combining those coefficients out front is another thing. And finally, last but not least, we have something that looks like this. Again, don't be surprised if you end up with more than one term in this case, and you can sort of tell because you see things that are base 5, and then you see something that is clearly going to be somewhere around base 3. In that case, just recognize you're probably going to have at least 2 terms. So I'm going to go through, and we have the negative square root of 27. Well, that's the negative square root of 9 times 3 plus 3 root 5 minus 80 is a little tricky because we need to find a number that divides into it that's a perfect square, and in this case we know that it's actually 16 times 5 subtract 2 root with 12, we're looking at 4 times 3. Wonderful. Now we can do all the square roots, so the negative root 9 is negative 3 root 3 plus 3 root 5. Subtract 4 root 5, subtract, well, the square root of 4 is 2. 2 times 2 is 4 root 3. And this will now lead to our final solution. You notice again we have a couple of root 5s and we have a couple of root 3s. So if we have negative 3 root 3 minus 4 root 3, we have negative 7 root 3. And we have a positive root 3 root 5. Subtract 4 root 5, which gives you a negative root 5. So again, those questions look tricky at first, but if you just follow your simple reduction techniques, you should have no problem in tackling any of these questions. Good luck. Bye.